Thank you for your kind introduction. I'm Yuka Iizuka from Nagoya Institute of Technology in Japan. Today, I'm going to talk about this topic. Chiral alpha beta acid are important motifs found in bioactive natural products, chiral ligand or catalysts, and building blocks. This structure can be efficiently constructed through enantioselective Mannich-type reaction of glycinate Schiff nucleophiles to imines. Many asymmetric additions of glycinate Schiff to aldimine have been reported. In contrast, only three asymmetric additions using cyclic ketimine, derived from saccharin and isatin, have been reported. These were accomplished using a copper or silver phosphine-type catalyst, where the catalyst activation of glycinate Schiff nucleophile play a crucial role. Despite these advances, there are no reports for the symmetric synthesis using acyclic ketimine, mainly due to the challenges associated with the formation highly hindered chiral center. On the other hand, we have recently reported efficient activation and enantioselective reaction of acyclic ketimino ester using our originally designed ligand binding heteroarenesulfonamide moiety. Heteroarenesulfonamide moiety contribute to the construction of advanced chiral bouquets. In 2024, we demonstrated the first asymmetric addition of thiol to acyclic ketimino ester to construct chiral N-essential structure and non-natural alpha amino acid derivative with quaternary chiral carbon center and a synchrono-alkaloid amide catalyst. Based on this finding, we designed a chiral ligand incorporating heteroarenesulfonamide moiety into chiral diamine phosphine framework as a novel catalyst. In this study, we report highly stereo and enantioselective synthesis of alpha-beta-diamino acid derivative center made possible by the development of chiral dinuclear catalyst. Okay, so I'm going to show you the detail of this reaction in the following slide. This slide shows our optimization study. We conducted ligand screening using CBZ protected acyclic ketimino esters and glycinate Schiff-based nucleophile as a model substrate. Under this condition, the reaction was performed using 10 mol% of silver acetate and 5 mol% of chiral PN ligand with 50 mol% of potassium carbonate as a base. When ligand A provided excellent result, affording the product 98% E, 99 to 1 ER, and 98 to 2 ER. Subsequently, we investigated ligand B and C, which replaced 2 pyridines from amino moiety with picoline amide and 8-quinoline amide. However, both ligands provide moderate width and low enantioselectivity. When ligand B with paired moiety instead of pyridine site was used, enantioselectivity dramatically decreased. Furthermore, ligand E lacking of phosphine moiety and ligand F with amine moiety instead of phosphine moiety, all of them exhibited side of diamine was protected by methyl group. Ligand X with carbonyl moiety was changed to imine form. However, both ligands were ineffective. In addition, previously reported phosphine-urea ligand I, which was employee in addition of Schiff to albumin, was tested. As a result, newly designed chiral ligand was shown to be superior. Also, the use of synchronous alkyl NMR ligand J, having a heteroarenesulfonamide moiety developed by our group, also led to low enantioselectivity. Next, we examine the other reaction parameter using ligand A. We first conducted the amount of silver acetate in entry 2 when silver acetate was reduced to 5 moles per analysis. Based on the reaction condition obtained from the optimization study, we next investigated the substrate scope. First, we introduced various electron withdrawing and donating substance on the aromatic ring of ketimine, achieving high level of enantioselectivity for this system, as well as substrate where the aromatic ring was replaced by non-sterile or heteroaryl and alkane group were also tolerated, leading generally to it high enantioselectivity. Substrate where the methoxycarbonyl moiety was replaced by ethoxy, isopropoxy, and benzoxycarbonyl moiety also gave the product in high enantioselectivity. Furthermore, nitride was reacted well, also providing the product with 94 to 6 years. In addition, we found that albumin and isatin ketimine were also tolerated in this reaction, also low stereocentricity. Next, we determine the absolute configuration of obtained product by X-ray crystallographic analysis. the compound in which introduced on the aromatic ring of ketimine was hydrolyzed by the treatment with 1 molar hydrogen chloride at various, and then any benzylation with 4-bromobenzoyl chloride provided corresponding product without loss of enantiomer purity. The absolute configuration of protected amine product was determined to be 2S trial isomer by X-ray crystallographic analysis. Next, we conducted gram-scale synthesis using model substrate, affording the aimed compound in 83% yield, 1991 DR, and 90 ER. And to demonstrate the synthetic utility of product, facet transformation was performed convert into 2-indole and dipeptide and alpha-beta-Diamino acid. First, the product compound using model substrate was hydrolyzed and transformed cyclic urea with triphosphane in 99% yield. Next, the condensation of product with both protected phenylalanine afforded a corresponding dipeptide in model yield. Furthermore, as a reaction of product where the methoxycarbonyl moiety instead was replaced by benzoxycarbonyl moiety with palladium carbon and hydrogen atmosphere, removed CBG and benzyl group, afforded protected amino acid in high yield and good stereoselectivity. To gain insight into the stereo control mechanism in this reaction by the novel dinuclear chiral catalyst, DFT calculations were performed using SCA-5R methodology. The result of energy profile for the formation of the nuclear complex was shown in this slide. It was found that the dinuclear complex is more stable than monometallic complex. In fact, this dinuclear complex was observed by ESI mass analysis. Also, interestingly, acetate anion was predicted to bridge two silver center and enable each metal center to activate reaction substrate strongly. Furthermore, 3D structure was shown here. It was found that phosphine moiety and heteroarenesulfonamide moiety of ligand formed the appropriate symmetric reaction site by taking the structure covered metal center. Next, proposed pathway for the reaction of model substrate was shown in this slide. Initially, nucleophile coordinate silver metal on the phosphine side to a photointermediate 2, which was observed by ESI mass analysis. Then, electrophile coordinate silver metal on sulfonamide side to a photointermediate 3. Deprotonation of alpha position of nucleophile by potassium carbonate as a base produce intermediate 4. Subsequently, the attack of nucleophile to electrophile produce intermediate 5. Finally, ligand exchange with potassium acetate to produce product and regenerate intermediate 1. Based on this assumed reaction cycle, DFT calculation for the transition state were performed. The calculation of transition state of 4 isomers were shown in this slide. The TS2S3R corresponding to major isomer was more stable than its enantiomer 3S, with difference in the transition state energy of 2.29 kilocalorie per mole. Also, the aromatic transition state were less stable by 3.33 and 8.98 kilocalorie per mole, respectively. Experimental result 1991 DR, 1982 ER, well agreed with theoretical calculation. Furthermore, to investigate the cause of stereoselectivity, we performed distortion interaction analysis. It was found that as a result, the interaction between the catalyst and substrate are most important for the cause of enantioselectivity. Furthermore, IgMH analysis was performed to investigate the key interaction between catalyst and substrate in major isomer. Green region indicates the weak interaction between catalyst and substrate. On the phosphine side, in addition to interaction with silver, CHO interaction between the aromatic ring of phosphine ligand and carbonyl oxygen of nucleophile were confirmed. Also, pi-pi interaction and pi-CH interaction were between the aromatic ring of phosphine ligand and nucleophile benzophenone were confirmed. On the heteroarenesulfonamide side, in addition, interaction with silver, pi-pi interaction mainly confirmed between the purging ring of ligand and aromatic ring of CPG group of electrophile. This finding demonstrated that this catalyst system exhibited high level of stereoselectivity through intricate interaction. In conclusion, we demonstrated the first asymmetric addition of acyclic ketimine ester and glycinate Schiff nucleophile to construct alpha beta amino acid derivative with quaternary chiral carbon center under our newly designed phosphine-Heteroarenesulfonamide Ligands. Experimental and calculated results using ASIR methodology reveal that newly ligand function as a dinuclear catalyst. Thank you for your attention.
Thank you very much for a very interesting presentation. We have time for one short question. Okay, so if there is no question for the audience, I will ask one. You showed a lot of experiments with the use of some basic compounds which are necessary to initiate the reaction. And in most cases, you use potassium carbonate as a base. You showed also some results with the use of some amine species as a base, amine. And have you tried any other bases, for example, sodium hydroxide or any other base? In other words, what was the reason you selected potassium carbonate?
Thank you for your question. Maybe potassium carbonate is not almost dissolved THF solution. Little bit potassium carbonate is dissolved THF solution. So racemization inhibited using potassium carbonate. Thank you.
Thank you very much. At the end, we have a certificate for you.
Thank you so much.
So please come here.